I would like to explain in this tape something about random variables that I think is quite confusing, and at least I got confused about it, so I would like to share. The thing is like this: there is two very similar expressions, but they mean totally something else. What is that? I'll write it down on a paper. Here I wrote it down. I'll show it on the screen. One is x times y, and one is z is equal to x times y. What is that? What is what am I trying to say? So I'm sure you bumped into the subject that's called joint distribution. Joint distribution means that there is I would like to explain it geometrically. There is a certain area that has a two-dimensional grid, like an X plane and a Y plane. In that area there are certain numbers. I'll make it. As you see, this is a certain area in the XY plane, and each point in this XY plane has fxy, and if you add them all together is equal to 1. So try to imagine like there is a piece of land, an irregular shape of land somewhere in the desert, and from this land there's a lot of tiny toothpicks growing out. One is smaller, one is taller. The total amount of the toothpicks of the volume is equal to 1, but each toothpick is a different height. The height of the toothpick is the fxy. So the point xy shoots out a toothpick, and according to the x and the y, there's a certain function that tells us the f of the xy. That will be the height of the toothpick. Now the area that this circle is drawn can be any numbers. Let's say it can go from the x-axis from 3 to 5, and the y-axis from 7 to 19. I'm just picking up numbers. It can be any numbers, any enclosed area that you can imagine, that the distribution, it can only be in this range of pairs x and y. Sometimes it's an irregular shape. Whatever it is this area, this two-dimensional area, that for all the possible values of x and y, and then you have f of xy that gives us out the function, and it teaches us how each single point, what is the height of that toothpick, and all these toothpicks together add up to 1. Okay, this is just simply explaining the concept of joint distribution. And self-understood, it is used in applications where x can be the height of a person in inches, y can be the weight, and then we can make a certain kind of diagram explaining how the distribution works, how many percent of this, how many percent of that. Bottom line is, the whole mountain and the valleys, whatever it is, must be equal to 1. That's a big rule in every single distribution. Okay, this is explaining the idea of joint distribution. So what does this have to do with x times y? If you see, I wrote here in the corner of the page, I wrote x times y. Answer is, you could ask, I know it seems queer, why should we ask and what's the point? But imagine somebody will ask you right now to multiply the x times the y. Now this doesn't make sense because you have to multiply it every single tiny dot. So the way to do it is you multiply every single x point times the y point times the f of the xy, that is this toothpick, the height of it, and also you make sure to give in this notation of dx dy. So you take it, I'm just trying to explain it in a very simple, in a very tangible manner. So you're taking each toothpick, you imagine it's a tenth of an inch by a tenth of an inch, and it has a height of 6 inches, another toothpick is 7 inches. All of them are a tenth of an inch by a tenth of an inch. That is the length and the width. So again, what you do is like this. You take each toothpick, you see where it's located. It's located on a certain point of x and a y, at least let's say the center of the toothpick. Let's use that as a reference point of x and y. You multiply the x times the y times the fxy, that is the height of the toothpick, times a tenth of an inch times a tenth of an inch. And you add together all these toothpicks. What does this give us? It gives us something that's called EXY. EXY is called the expected value of x times y. So actually what we're doing here is, just like there's an expected value if you have only an x, here we're taking all of the x's and the y's. Since it's a joint distribution, we have a right to take the x multiplied by the y and then multiplied by the fxy, and finally make it, just to minimize it as tiny as possible, we'll use a tenth of an inch times a tenth of an inch. That's going to give us an expected value of jointly x and y together. It's hard to understand what value this gives us. It looks like very theoretical, but you could do that. So this is, in a certain sense, the idea of an expected value of this function that we could call it this joint distribution of x and y. Now we can do something totally different. I'll start it in this video and I'll continue the next one. Instead of making a joint distribution, we create something, a new distribution. It is called z is equal to x times y. As you can see in what I wrote in the bottom. What is that? Z is equal to x times y means like this. Again, I start off with the same core. I have this circle, and I have there, I choose a certain two-dimensional plot on the ground. They have certain values of x and y are enclosed there, and then there's also certain toothpicks there, certain heights, all fine. What is the difference here? Here, what we wish to do is, we are trying to make something, create something new out of this thing, out of this whole situation. What we will do is, imagine I'll continue this in the next video. Please, I'm apologizing for this stuff.